When you look up at the sun, it's easy to just think, yep, giant ball of fire. Seems pretty straightforward, right? But here's the thing. For the longest time, the actual physics of how our sun shines was this huge, impossible puzzle. I mean, a real head scratcher. Turns out the answer isn't really about fire at all. It's about this bizarre little loophole in the very laws of reality. So let's dive into this quantum mystery. Okay, so let's just jump right in with a pretty wild question. Why should our sun actually be dark? I know, it sounds crazy, but if you only use the normal rules of physics, the ones that make sense in our day-to-day lives, our star just isn't hot enough to light up at all. Seriously, based on everything we thought we knew, it should just be a huge, cold, dark ball of gas floating out there. All right, now let's talk about the sun's core. Our best models tell us it is just unbelievably hot. We're talking 15 million Kelvin. To put that in perspective for you, that's over 27 million degrees Fahrenheit. I mean, that's a temperature it's almost impossible to even wrap your head around. But, and this is the unbelievable part, 15 million degrees, it's way, way too cold for nuclear fusion to get started. So think about that. We've got a star that is very obviously shining, right? But according to the old rulebook, it doesn't have nearly enough heat to even light its own fuse. So how is that even possible? Well, to figure this out, we've got to pop the hood and look at the sun's engine. It's a process called the proton-proton chain. And believe it or not, understanding how it's supposed to work actually makes this whole temperature problem seem even worse. Okay, so this is basically a 3-step recipe for making starlight. Step 1, you take 2 protons and you smash them together so hard that one of them actually turns into a neutron. That creates a new thing called deuterium. Then for step 2, another proton comes along and collides with that deuterium, creating helium-3. And finally, 2 of those helium-3s fuse together. What you get is stable helium-4, and it kicks out 2 protons to start the whole cycle all over again. And here's the magic. Every time this cycle completes, a little tiny bit of mass vanishes and becomes a huge burst of energy. But there is a massive, gigantic problem with that very first step. It smacks right into a fundamental law of the universe. It's like this invisible force field that should stop fusion dead in its tracks. We call it the Great Repulsion. So this roadblock is officially called the Coulomb barrier. And it's pretty simple, really. All protons have a positive charge, right? And what do 2 positive charges do? They repel each other with a ton of force. Seriously, just imagine trying to slam the north poles of 2 super powerful magnets together. It's like that. For these protons to actually fuse, they have to get so incredibly close that a different force, the strong nuclear force, can grab them. And that means they have to somehow smash right through this powerful, invisible wall of repulsion. So how much energy are we talking about here? How much oomph does it take to just brute force your way through that barrier? Well, according to classical physics, you'd need a temperature of about 5 billion Kelvin. 5 billion, with a B. But remember what the sun's core actually is? It's only 15 million Kelvin. That's not just a little off. It's not even in the same ballpark. It's a totally different sport. So, how in the world does the sun pull it off? The answer, it turns out, isn't in our nice, neat, everyday physics. Nope, it's in physics' strange, mind-bending, and let's be honest, just plain weird cousin, quantum mechanics. There's a loophole in the rules, a kind of quantum ghost in the machine. Okay, to get this loophole, you have to completely change how you think about a proton. It's not a tiny, solid little ball. In the quantum world, it's more like a cloud of probability. It's called a wave function, and it basically just maps out all the places the proton could be. It's fuzzy, it's spread out, and it isn't really in any one single spot until you actually measure it. And this is where it gets really mind-bending. This whole fuzzy, cloud-like nature makes something possible that sounds like science fiction. It's called quantum tunneling. See, because the proton's location is just a wave of probabilities, there's a tiny, but not zero, chance that part of that wave actually extends through that repulsive wall. So instead of needing all that energy to climb over the wall, the proton can just, poof, appear on the other side. It doesn't break through the wall, it just tunnels straight through it, just like a ghost. Now, this isn't just some quirky little theory for a textbook. This quantum trick is how the completely impossible becomes absolutely inevitable. It's what powers our sun, it powers our whole solar system, it's the reason we're even here. It all comes down to the sheer scale of what's happening. But let's be really clear about something. The chance of any one pair of protons actually doing this, actually tunneling through, it's absurdly low. I mean, it is so close to zero, you might as well call it zero. For any single collision, it's basically guaranteed to fail. But this right here is the whole secret. The sun's core is just crammed with a number of protons you can't even imagine. And they are all smashing into each other constantly. We're talking about 10 to the power of 38 collisions every single second. That's a 1 with 38 zeros after it. It's just a staggering number. So what happens when you take a chance that's practically zero and you try it an almost infinite number of times every second of every day? Well, that impossibly rare event starts happening all the time. That's how you turn a no way into a definitely. All of those super unlikely little successes add up, and they produce the sun's absolutely staggering energy output, 3.8 times 10 to the 26 watts. That is the sunlight that powers everything on Earth. And you know what? This whole quantum process also explains why the sun has been around for so long. That very first step in the chain, where one proton flips into a neutron, that's controlled by something called the weak nuclear force. And it lives up to its name. It's super, super slow and not very efficient. And that's a good thing. This inefficiency is like a cosmic safety valve. It throttles the sun's fuel use, making sure it has a nice, slow, steady burn for billions of years, instead of just going off like one giant bomb. So when you really boil it all down, it comes to this. Our entire existence, everything, it all hinges on this one bizarre, wonderful loophole in the laws of physics. The warmth you feel on your skin, the light that grows our food, the energy that powers our entire world. It's all thanks to protons acting like little ghosts and just showing up where they're not supposed to be. You know, this whole thing just goes to show how truly strange and counterintuitive our universe really is, down at its most fundamental level. It's an incredible reminder that the line between what we think is impossible and what's inevitable, well, it might just be a matter of probability and a whole lot of chances. And that leaves us with one last really fascinating question to think about. What other cosmic impossibilities are being made real right at this very moment by the weird and wonderful rules of the quantum world?